Hello, I'm Mohammed Arashi, and I'm going to explain about estimable linear functions and the very well-known Gauss Markov Theorem in linear modeling. Here we have a definition for estimable linear functions. We say that the linear function of the parameters q prime b is estimable if it has an unbiased linear estimator. It means that there exists t prime y, which the expected value of t prime y is equal to q prime b. First of all the vectors here are column vectors. So t prime y is a scalar, q prime b is a scalar. We assume that b is a vector of parameters. So the linear function is defined as q prime b, and y is the observation, and t prime y is a linear function of observations. So a linear function of parameters is said to be estimable if you can find a linear function of observations that the expected value is equal to the linear function of parameters. In order to see, let's add some examples here. Suppose that the expected value of y is actually, let's say, assume we have a t-dimensional vector, column vector, and the expected value is given by alpha plus beta minus gamma, some parameters, alpha plus beta minus gamma, again for y2, and alpha plus beta plus gamma. Okay, in order to illustrate the concept of this definition, let's consider some examples. So here we have examples. We consider t prime y. I use t for the transpose notation, and then the consequence expected value of t prime y equal to q prime b. This is here we want to illustrate the concept of estimable linear function. For instance, in this example, specific example, y1 is equal to 1, 0, 0, y, which indeed gives alpha plus beta minus gamma according to this definition here. Then y2 is equal to 0, 1, 0, because it's the second element of y. So simply if you multiply by the vector y, here the vector y is y1, y2, y3. If you multiply this vector with y2 is obtained, and simply you see the expected value of y2 is the second element here, so it is alpha plus beta minus gamma again. Also y3, 0, 0, 1, if you multiply by y, remember it's a column vector, you transpose it and then you multiply to the column vector here y, you get alpha plus beta plus gamma. Okay, so also if we sum y1 with y2, then we have 1, 1, 0. You see, if y is y1, y2, y3, and you multiply this row vector with y, then the resulting is y1 plus y2, which is a linear function of observations, or better say a linear function of y. Here y1 is a linear function of y, y2 is a linear function of y. So everyone is a linear function of y, and the resulting is simply when you add y1 plus y2, you will get 2 alpha plus 2 beta minus 2 gamma, if you add these two together. Another one is half y1 plus y2. I will carry this example towards the ends of this session. So let's keep everything in mind. So I define this linear function of observations, and the linear function of estimator is this guy. And also half y2 plus y3. Then it is half 0, 1, 1y. Once again, if you want to add the second element with the third element of y, you use the vector 0, 1, 1 with y, and then half here. The resulting linear function of parameters is alpha plus beta. Also, we can also say, okay, half y3 minus y2, which is half 0 minus 1 1 y, and it is then equal to gamma, huh? So gamma is actually a linear estimable function of the parameters, because you can find a linear function of observations which the expected value is equal to gamma. However, there is no better said t prime y such that the expected value of t prime y is equal to alpha, or there is no t prime y such that the expected value is equal to beta. So these two parameters, alpha and beta, they are not estimable functions. Estimable functions. So you see, for some functions of parameters, we can find estimators. We can for this function of parameters, we can find this estimator. For this function of parameters, we can find this estimator, and so on and so forth. Till alpha and beta. For alpha is not estimable, beta is not estimable for this specific example. This is important to keep in mind. Okay. Now we know the definition. Now we go to the theorem, and in this theorem we say Q prime B is estimable if the rank of X is equal to the rank of X augmented with a row Q. So if you have an augmented matrix, remember Q is a column vector, Q prime is a row vector. So if you add this row vector and augment it with the matrix X, if the rank of this augmented matrix is equal to the rank of X, then you would say Q prime B is estimable. Once again, let's consider. Let's go back to this part and see what will happen here. Okay. For our problem, according to this parameters, I can simply write it. Let me change the color. I can simply write it as, if I erase this part, I can simply write it as a matrix 1 1 minus 1 1 1 minus 1 again 1 1 1 multiply by the vector alpha beta gamma. And here in this design matrix, if you look at it, we have two independent columns. These are the same. These two columns are the same. So we have two independent columns. So the rank of matrix X is equal to 2. So I can call this matrix as X. Not write it here. Let's suppose this is X. This is matrix X, and this is the expected the vector of parameters B. So let's write B here in order to avoid confusion. So it is XB, and the rank of X is equal to 2. So let's keep this in mind. For this specific example, the rank of the design is equal to 2. So rank of X is equal to 2. Let's work with this guy. Let me go back with the color. And then the augmented matrix. If I construct the augmented matrix, it is q prime x, which means that I consider a vector q. Let's write it here. So we have q1, q2, q3, since we have three columns. So the augmented matrix is q1, q2, q3, the transpose of this column vector, and then you have your design. Yeah, this is the augmented matrix. If, according to the theorem, let's go back to the theorem once again. If the rank of this augmented matrix is equal to the rank of x, then q prime b is estimable. It means the rank of this matrix must be equal to 2. So we must have rank of q prime x equal to 2. It means that according to this structure, q1 must be equal to q2. So that is the result. Now let's go to examples. Let me add another page. Okay. Once again, we consider the same example. I said we're going to carry that example up to the end. So we have the expected value of t prime y equal to q prime b. And we're going to consider the case where q1 is equal to q2. For instance, the one that alpha plus beta minus gamma, consider this linear estimable function. We had it as a linear estimable function. If I go back, alpha plus beta minus gamma, you will see alpha plus beta minus gamma. This has this, linear function of observations, this linear function of observation, and this linear function of observation. So we have three different linear function of observations y, which we can use to estimate alpha plus beta minus gamma. So alpha plus beta minus gamma, you can write it simply like 1 minus 1b. Suppose your b is alpha beta gamma, as I wrote already, and we must conclude that q1 is equal to q2 according to the previous result, and in any case that q1 is equal to q2, you have estimable function. So from previous example, we have here the possible estimators. Let's look at the possible estimators. The possible estimators here, y1, 1, 0, 0, y, and y2, 0, 1, 0, y, and also half y2 plus, y1 plus y2. If you remember from the slides above, these are the linear estimators. And here you see this element is 1 and this element is 1, so we conclude that q1 is equal to q2. But we showed that we had three different linear function of observations in order to estimate alpha plus beta minus gamma. And you see these are the possible estimators. And in this example, q1 is equal to q2 is satisfied. For another one, let's consider another one. For instance, alpha plus beta plus gamma. In this case, once again, this one is 1, this one is 1, so q1 is equal to q2. It is not important what is this third element. The third element is not important. According to the specific example that we had, q1 must be equal to q2, for which the rank of the augmented matrix is equal to the rank of x. And in this case, if you remember, this was the linear function of the observation. But let me write it in red. But if you remember, we didn't have you know, linear functions of observation in order to estimate alpha or beta. Now let's look at alpha. How can you get alpha? You can get alpha if you put the first element equal to 1, second element 0, third element 0. And you see, in this case, we conclude that Q1 is not equal to Q2. So we conclude that it's not estimable. Huh? So we see that the condition is not satisfied, and we already show in the example that for this specific linear function of parameters, you do not have estimator. Now let's go to the proof of the theorem. Proof of the theorem is pretty straightforward. I will also explain about the implication of this. I will explain it in details. But let's first look at the proof. So for a moment, forget about this implication and the result. Let's look at the proof of the theorem. The proof is pretty simple. According to the definition, you will say Q prime B is estimable if and only if there exists T or a vector which the expected value of the linear function of observations is equal to Q prime B. But remember from the model, the expected value of T prime Y, T is fixed, it's not random, so it goes out. Factors or goes out from left hand side from the expected value. So it is T prime expected value of Y. So it is equal to T prime expected value of Y. But the expected value of Y is equal to XB. So it is equal to T prime XB. And we know that it must be equal to Q prime B because Q prime B is estimable. So the expected value of T prime Y is equal to Q prime B. So we get this equality. From this equality, you can conclude that it happens if and only if Q prime is equal to T prime X for some T. And this is actually coming from the application. For a case that the rank of X is equal to P, all linear functions of the parameter are estimable. Because the conditions of the theorem is always met for this specific case. Now, what does this guy say? When Q prime is equal to T prime X, the Q prime B is a linear combination of the rows of XB. This is what we want to say. So look at this implication. Now let's go and once again add a page and consider the implication for this theorem. Once again, the implication is the Q prime B, as I said, is a linear combination of the rows of XB, and this is the result. Now let's go look at the example again. So we have the y1, y2, and y3. I'll quickly write it again. Alpha plus beta minus gamma, alpha plus beta minus gamma once again, and alpha plus beta plus gamma. For a moment, I use the abbreviation row 1, R1, and the row 2, I use the abbreviation R2 here, and row 3, I use R3. I want to construct the condition. If you add row 1 and row 2 or row 1 and row 3, the condition satisfied. Huh? So let's look at the structure. Q prime B and then the T prime XB. Once again, Q prime B is a linear combination of the rows. If I can show that, then it shows that it is an estimable function. Here I have it. For instance, alpha plus beta minus gamma. So if I have row 1 plus 0 row 2 plus 0 row 3, or I have 0 row 1 plus R2 plus 0 R3, or remember from the example, half R1 plus half R2 plus 0 R3, then it shows that this linear function of parameters is a combination of the rows. And you can simply check from the previous result. If I go up, you will see here we discuss details. You see here we discuss the details. Huh? So coming back for another one. For instance, the alpha plus beta plus gamma. In order to see that it's an estimable function, according to the implication of the theorem or the proof, you can write it as 0R1 plus 0R2 plus R3, which is equal to R3. So by R3 you can find it. Or the other one, 2 alpha, if you remember, 2 alpha, 2 beta minus 2 gamma. It was actually sum of first two rows. So it is R1 plus R2 plus 0 R3. Or even gamma. If you remember, gamma was estimable function of parameters. Because you can write it as 0 R1 minus half R2 plus half R3. However, there is no linear combination of the rows in order that you can get alpha or beta. So no linear combination. No linear combination of the rows of XB. Once again, remember X, I tried to use, I denoted the design as X and this vector parameters as B. So there is no linear combination of the rows of XB that yields, for instance, alpha or beta. So these are not estimable functions. So it's pretty straightforward, and we could easily understand the definition in order to for an estimable linear function, and also the use of the theorem and its implication. I'm gonna record video in order to save the volume of that. Thank you.